This is a qubit. You're probably familiar with its cousin, the bit. It's the fundamental unit of information, a 0 or 1, used in classical computing, such as in the device you're using to watch this video. You might have also heard that qubits are both 0 and 1 at the same time, in superposition. While this is true, what does it actually mean, and how does this make qubits and their quantum computers useful to us? By the end of this video, you'll know how we properly represent qubits in block spheres, and how we can manipulate a single qubit using quantum gates, the Pauli X, Y, Z and Hadamard gates, with plenty doses of animation and maths along the way. To dive into quantum gates, let's first take a look at logic gates using normal bits. If bits are the lowest level of a computer system, these gates make the bits work together. The three most common classical logic gates are NOT, AND, OR. The NOT gate, represented by a triangle with a circle at the tip, simply takes in one bit and flips it. If it receives a 0, it outputs a 1, and if it receives a 1, it outputs a 0. The AND gate takes in two bits, A and B, to output Z. If both A and B are 1, it outputs a 1, or else it outputs a 0. For the OR gate, if either A or B is 1, it outputs 1. Used together, these can manipulate millions of bits and execute very powerful algorithms. Note that while the NOT gate is reversible, that is, if we know what the output Z is, we can find the input, the AND and OR gates are not reversible. If we know what Z is, we cannot always find what A and B are. We lose some information when we apply these gates to bits. If Z is 0, we don't know what the values for A and B are. Which one, if not both, are 0? Keeping this in mind, let's take a look at a qubit. To represent a qubit, we draw a unit sphere, and we have, similar to bits, two basis states, ket 0 and ket 1. Under this bracket or Dirac notation, if we wanted to represent the 0 bit, we would just have to draw a straight arrow from the sphere's center to the North Pole. If we wanted to show that 1 bit, we would draw a straight arrow to the South Pole. In matrix form, ket 0 is 1 0, and ket 1 is 0 1. This will come in handy later for quantum gates. These poles are the only two spots available on the sphere to the classical bit. The rest of the space is for qubits only. We can label the x-axis of the sphere with ket plus and ket minus, and the y-axis of the sphere with ket I and negative I. To learn more about I, the imaginary number, click on the pop-out banner above. These axes give the qubits extra properties under phase, and so a qubit in superposition could look something like this. Superposition just means a combination of 0 and 1 on the sphere, anywhere in between. Altogether, we call this diagram to represent qubits the Bloch sphere, from the concept introduced by Felix Bloch. The trick is, when we finally measure a qubit, it will either be in state 0 or state 1. The closer up this arrow is to ket 0, the higher probability this qubit will collapse to 0 when measured. And likewise, the closer down an arrow is to ket 1, the higher probability of measuring a 1. We can describe this with the equation alpha ket 0 plus beta ket 1, where alpha and beta are complex probability amplitudes. Simplified here, alpha and beta tell us how likely a qubit is to collapse to 0 or collapse to 1 when finally measured. To present this graphically on the Bloch sphere, this equation tells us our angles. Alpha is cos theta over 2, and beta is e to the I phi sine theta over 2. In our diagram, theta is the angle between the z-axis and the vector, and phi is the angle in the xy plane, like so. Now we understand how qubits are represented graphically, let's take a look at our first quantum gate, the Pauli X gate. In matrix form, this is 0 1 1 0. Pretty much doing what it says on the tin, it describes a rotation of pi radians, halfway around the x-axis. For example, if we had a qubit pointing to the 0 state, the X gate would rotate this pi radians around the x-axis to get the qubit pointing to the 1 state, like so. We can see why when we perform the matrix multiplication. Our input qubit was the 0 state qubit with the matrix 1 0. Making sure the transformation matrix is applied before this, we can multiply them together to receive 0 1 as the output qubit, which is the one state. Given this property of flipping between the two states, it's often referred to as the NOT gate for qubits. We can also apply the X gate to superposed qubits. For example, this qubit would be transformed to the opposite side of the x-axis. This one. Moving on to the Pauli Y gate, it's represented by the matrix 0, I, 0. Again, this just represents a rotation of pi radians around the y-axis. For example, this superposed qubit will transform into this one, halfway around the y-axis. Similarly, like before, if we have a basis state qubit, applying the Y gate will flip it to the other base on the opposite side of the axis, like so. This gate is unique among the Pauli gates, given it's the only one which features the imaginary number, I, and so can phase shift qubits, which comes in handy for quantum error correction. The last of the Pauli gates is the Z gate, represented by the matrix 1, 0, 0, -1. This causes a qubit to rotate pi radians around the z-axis. For example, a qubit pointing along the positive y-axis, like so, will rotate halfway around the z-axis to point to the negative y-axis. This just means the Z-gate doesn't change the probabilities of measuring a 0 or 1, it just changes the phase of Ket1. Now, also note, if we apply the Z-gate again to this qubit, we just receive our original qubit. Altogether, these are the Pauli X, Y and Z gates, rotating qubits pi radians about their respective axes. Importantly, in comparison to the classical gates we took a look at before, such as AND, OR gates, all of these quantum gates can be reversed. The reversibility, due to all of these matrices having an inverse, means no information is lost during a quantum operation. On to the most crucial single qubit gate, the Hadamard gate, represented by the matrix 1/√2, 1, 0, 0, -1. This is integral to quantum operations, as it creates a superposition from basis states. The Pauli gates we looked at before flip between the basis states or rotate already superposed qubits, but they don't place a basis state qubit into superposition. Hadamard gates do. It does this by rotating a qubit pi radians around this axis, the axis in between the x and z planes. For example, a qubit in the 0 state will be transformed to the qubit pointing along the positive y-axis, like so. An equal superposition is created between the 0 and 1 states. If we were to apply this gate again, it would simply rotate pi radians back around to return to the original basis state. The same occurs for the qubit initially pointing to the 1 state. It will be superposed pointing to the negative y-axis, and so if measured now, the qubit will be equally likely to collapse to a 0 or a 1. This property of creating equal superpositions is crucial in quantum circuits, initializing qubits at the start of quantum algorithms, paving the way for other qubit gates to act. For example, it's necessary for the quantum Fourier transform and subsequently at the heart of the popular Grover's and Shor's algorithms. Today, we focus on the quantum gates that manipulate a single qubit, but to grasp hold of all quantum phenomena, such as entanglement and interference, multiple qubits need to be used, entering into the exciting domain of multi-qubit gates, such as CNOT, and oracle and diffuse operators. Thanks for watching, beat the calculator.